So last time I talked extensively about one qubit operations, which include the x, y, and z operations, and also a special combination of x and z called the Hadamard operation. So today I'm gonna start talking about the two qubit operation. And most important of the two qubit operation is the Cnot operation. So today I'm going to talk about the two kinds of two qubit operations. One is called the Cnot, and the other one is called the swap operation. Okay, so Cnot, and if you have any background in electrical engineering, you probably know that this is not a language that came up in the quantum computation. In fact, C0 is a familiar operation also in the classical computation. So C0 stands for controlled not operation. So a not operation, which I designated as X before, simply flip the state of a bit from 1 to 0 and 0 to 1. But the Cnot operation involves two qubits. One is the control bit, and the other one is called the target bit. And what the Cnot does is when the first qubit is 0, then it does nothing to the second qubit. So no matter what y is, whether y is 0 or 1, there's no change in the overall two qubit state because the first qubit was in the 0 state. But if the first qubit was in 1 state, then the Cnot operation will flip the state of the second qubit from y to its negation. So y bar means that if y is 0, then y bar is 1. If y is 1, then y bar is 0. Okay, so it's a not operation on the second qubit, but it's only doing that if the first qubit happens to be in the 1 state. And the not operation does not switch on if the first qubit is in the 0 state. So a kind of mathematical way of writing that all down is as a tensor product. If the first state is in the 0, 0 state, then the operation on the second qubit is just an identity, it does nothing. But if the first qubit was in the state 1, then the action on the second state is represented by the X operator, which is the negation. Okay, so to sum, Now, the matrix representation of this is, you can work this all out quite easily. So the matrix representation is 1, 1, 0, 0. Actually, let me do it in a more elegant way. Because the state 0, 0 will have a matrix representation like this, and the state 1, 1 will have a matrix representation like this. Okay, so this means that 1, 0, 0, 1 cross I, and that means 0, 0, 0, 1 cross X. Now, according to the rule of building up a tensor product, then we have this identity, 2 by 2 identity matrix in place of the 1. And we have the X matrix in place of the 1 over here. And adding these two together, we get an identity matrix in the upper left corner of the 4 by 4 matrix, and X matrix in the lower right corner of the 4 by 4 matrix. So this is how you represent the Cnot unitary operation as a matrix. Okay, of course Cnot is a classical operation. It does not bring about entanglement. And you can also check that from the fact that you Cnot operating on the 0, 0 is 0, 0. So it basically maps one tensor product state to a different tensor product state. Okay, it never maps a tensor product state into some entangled state. And this explicit writing down of the operations on all the states makes that point clear. Well, of course you can use the second qubit as the control and the first qubit as the target. Okay, there's no what you call the control qubit and what you call the target is really just a matter of choice. And when you switch the role of the control and the target, then the corresponding matrix will be, the corresponding operation will be written in a slightly different way. So if the second state is in the 0 state, then you do nothing on the first qubit. And if the second qubit is in the state 1, then you apply negation to the first qubit. Okay, so that is this, and x is that, and this one over here is 0, 0, 0, 1. So when you take a tensor product of these two matrices, you get one. You get that, and then from this second tensor product, you get the okay, and now you just have to add these two together to find the overall unitary matrix, which is 1. Well, okay, it's a little bit boring to write them all out, so maybe you should do it yourself. Okay, so let me write this as a u prime, and the previous Cnot operation as a u. So if we do this u and u prime operation, u Cnot operation and the u prime Cnot operation in succession on some sort of state, and each state also has a column vector representation of in terms of these 4 numbers, right? Because A is the coefficient for the 0, 0 state, B is the coefficient for the 0, 1 state, C is the coefficient for the 1, 0 state, and D is the coefficient for the 1, 1 state. Okay. So given this initial state, let's say you first apply the conventional Cnot operation, followed by the reversed Cnot operation, where the second qubit is the control and the first qubit is the target. Then the result can be represented as some new column vector with coefficients a prime, b prime, c prime, d prime, which is obtained by two matrix multiplications on the original state vector a, b, c, d, where these are the matrix elements of the conventional C0 operator, and these are the matrix elements of the reversed C0 operator. And both operators in their matrix forms have been written down previously. So doing a unitary operation in succession is the same as doing a matrix multiplication in succession. Okay, so that's why, so there's this close one-to-one correspondence between a matrix multiplication of linear algebra and unitary operation, which is a physical operation performed on a physical quantum state. Okay, maybe a nice bit of mathematical knowledge, or maybe I should say mathematical know-how, is the following. You can prove that the product of these three matrices, where Hadamard was, if you remember, is the sum of the x and z matrices. So if you do multiplication by Hadamard to the left and the right of the x operator, in fact, x becomes a z. You can also prove that HZH is x. So Hadamard operation is a change of basis operation, as I said. And in the new basis, x looks like a z and z looks like an x. And that's what the change of basis often does to the representation. Okay, so now by implication, when you do a Hadamard on the second qubit, leaving the first qubit unchanged, then the action of such a unitary operation on the C0 which would be this. So this is a unitary operation on the unitary transformation on the unitary matrix. And U is given here, so I cross H to the left. And U C naught was I cross what? Sorry. U C naught was 0, 0, cross 1, plus 1, 1, cross X. And U dagger, in fact, you can check that U dagger is the same as U. Okay? And the result of this multiplication you can figure out by doing the matrix multiplication on the first qubit and the matrix multiplications on the second qubit separately, and then taking the tensor product of the individual outcome. So if you do the, well, this is just identity, so it does nothing. So the result would be still 0, 0. However, for the second qubit, you're doing this Hadamard unitary transformation, but then you're doing this on identity. So identity will always be an identity, so there's no change. Okay, now let's go over here. So this is 1, 1. That doesn't change because you're not changing the basis of the first qubit. But now finally you're doing some meaningful change of basis operation on the second qubit. Okay, and that's what you're doing. And HXH is equivalent to Z, as we just showed. So the consequence of performing the change of basis on the second qubit is that what was once an X matrix over here now becomes a Z matrix. In other words, this becomes a controlled Z operation, not a controlled X operation. Okay, so the control Z operation and the control X operation, or the Cnot operation, are in fact the same operations, just written out in the different bases. And I thought that this is perhaps worth keeping in mind. Okay, so the other bit of interesting 2-bit operation is the swap operation. So it literally swaps or interchanges the state of the 2 qubits. So I give you this tensor product of the 2 qubit states, and the result is that the contents of the states are interchanged between the 2 qubits like this. Okay, now there must be some sort of matrix representation of this swap operation. And to figure out, first it's useful to write down these operator explicitly in this basis. So the swap operation acting on the 0, 0 will just give back the 0, 0. However, the swap operation acting on the 0, 1 will return 1, 0. And swap acting on 0, 1 will return, confusing always. Swap operation acting on 1, 0 will yield 0, 1. Swap acting on 1, 1 will yield 1, 1. Okay, now the next stage is to turn this into a explicit matrix. Okay, so 0, 0 has this column vector representation of 1, 0, 0, 0, 1, 0, 0, 0. Okay, and 1, 0 has the column vector representation like that, and 0, 1 has 0, 1, 0, 0 representation, and 0, 1 state has this vector representation. 1, 0 has this vector representation, and finally this. Okay, so you work out each of these matrices by multiplying a column with a row vector and add them all up to find that the result is the following: 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, and 0, 0, 0, 1. Okay. Now, it's an interesting challenge to check that this matrix is equivalent to the following tensor product. Okay. And you're invited to check this fact by explicit calculation of all of these tensor product. And then by adding these four tensor products together and dividing by 2, you get to recover this matrix. Okay? But in the conventional spin language, this is nothing but the inner product of two Pauli matrices. Okay? So this swap operation, use swap operator, finds a nice operator expression as the inner product of two Pauli matrices, one coming from the first qubit, the other one coming from the second qubit, with an extra factor extra factor 1 to correct for the overall normalization. Well, in magnetism literature, this sort of interaction between a pair of spins, let's say you have a spin at side I, another spin at side J, and these spins interact via this sort of interaction. This is known as the Heisenberg interaction in solid state physics. Okay, and this is one of the most interesting and most important interactions in condensed matter, because spin systems that are governed by such interaction can give rise to all kinds of exotic physics, especially in low dimensional systems, one dimensional and two dimensional systems in particular. And so this is a very important kind of interaction in solid state physics, but it also turns out that this has an interesting identity to a swap operation by this mathematical identity, which I have just proven. So changing the content of the two spins, one at site I and the other one at site J, is equivalent to the Heisenberg interaction up to an overall constant. But notice that the swap operation does not entangle state. Okay, I mean, that's kind of obvious from the definition. That is, if you have some sort of a state at the side I and state side j at the side j, then all that the swap operation does is simply interchange the contents of the states. But still, a product state remains a product state after the swap operation. So this Heisenberg interaction turns out to be a pretty simple interaction from the entanglement perspective, in the sense that this does not increase the entanglement in the system. However, a bunch of spins that are interacting through this interaction is called the strongly correlated systems. And usually a bunch of spins that are interacting through this Heisenberg interaction uh, provides a huge challenge to theorists and experimentalists trying to figure out just exactly what the true ground state of such a system is. So it's a very complex problem, but it's not necessarily a complex problem from the entanglement perspective. As you can see from this simple observation that the swap operation is equivalent to the Heisenberg interaction, and swap operation is not an entanglement changing or entanglement creating operation at all. So perhaps this statement is not going to ring a bell to you immediately, but I just like to emphasize for the record that the entanglement and correlation may not always be equivalent words.